Problem 12. Problem 12 is an interesting problem because it has multiple objects, friction, and also involves an inclined plane. The first thing you need to do in any given problem is decide what kind of methods that you're going to use to solve it. Kinematics, force, energy, momentum, etc. In this kind of a problem, number one, the inclined plane is a partial clue, but more to the point, the real clue as to how this is to be solved is the fact that it involves questions regarding tension and acceleration. If we were to solve the problem with methods other than forces, for example energy, the tensions themselves would not even appear in our equations, and F equals ma is certainly the most direct way to get at acceleration. So for that reason, we will solve this problem with force methods. Now, when you deal with a problem in force methods, you don't really concern yourself to first order approximation with what you're asked as you perform the solution. Instead, you simply analyze the problem in the normal way, list the objects, free body diagram, resulting equations, and then the equations themselves will yield some answers. Looking a little more closely, what we find when we see this problem is that there are three objects. These objects are the 1 kilogram mass, the 2 kilogram mass, and the 5 kilogram mass. What this means is that when it's time to set up our free body diagrams and follow them with equations, we know that the number of equations we get will always be equal to the number of dimensions we have among our free body diagrams. And so we see that the 1 kilogram object will yield a two-dimensional free body diagram, vertical with normal and gravity, horizontal with tension and friction. The 2 kilogram object will also yield a two-dimensional free body diagram. These will not be directly vertical and horizontal coordinates as it's tilted on an inclined plane. However, there will be two dimensions resulting in two equations. And finally, our friend the 5 kilogram object, which is really the one driving the system, it's so much more massive, hanging there in gravity, will be producing only a one-dimensional free body diagram, and that one-dimensional free body diagram will just be the vertical coordinate. So counting these up, we see we have a total of 5 dimensions in the problem, meaning that this problem will be solved by 5 equations, with 5 unknowns, and in fact the questions that I just cut away so that you can't even see them are 5 individual questions asking for those unknowns. Let's proceed. The first step in every force problem is to draw a free body diagram, and we're going to do so in the order in which I've highlighted these objects, beginning with the 1 kilogram object. This dot represents the 1 kilogram object, and to draw the free body diagram we simply list every force, be careful to never leave one out, that act on the 1 kilogram object. So the first force that might occur to you is gravity, which is 1g downward. The next one is a contact force because this 1 kilogram object is resting on a surface. Contact forces always have a component that is perpendicular to the surface, and we use the mathematician's word for perpendicular, which is normal. And so we call that the normal force. I'm going to call it N1 because I recognize that the 2 kilogram object is also going to be providing a normal force because it's on a surface. And in order to keep everything straight, I need to have a good notation. The second thing resulting from a contact force at a surface is possibly a horizontal component. You decide whether you get a horizontal component by looking for friction. We see in this problem we do have friction, which is mu sub k equals 0.2, and so we will have a frictional component to this force. Now, friction opposes sliding. Since the 1 kilogram object will slide to the right, we're going to have a frictional force that will go to the left, and the strength of that frictional force will be mu k, which was 0.2, times the appropriate normal force, N1. Finally, there's one more thing we haven't accounted for. We haven't accounted for the fact that there is a string tied to the object. The string creates a tension, and tensions always pull, meaning that the tension T1 is applied directed to the right on this object of 1 kilogram mass. Looking carefully at the free body diagram before we proceed, we ask ourselves whether it has all forces accounted for in the diagram: gravity, contact in the form of two components, tension. That's it. So, the second step in drawing your free body diagram after listing all forces is to orient the coordinate system. And what we always try to do is orient the coordinate system in such a manner that the equations will be maximally simple, and thereby the algebra that's required from us at the next stage is the easiest possible. And the way we ensure that is we identify the direction in which the object is accelerating, and we align the coordinate system with that direction. We know the 1 kilogram object will be accelerating to the right, so we're going to make our coordinate system on top of here with a positive direction towards the right, meaning negative towards the left. And since it's a two-dimensional free body diagram, the second coordinate has to be perpendicular to the first. So since the first was horizontal, the second is vertical. This free body diagram, being two dimensions, will yield two equations, and they're going to be simple equations because all of the forces are aligned nicely with the coordinate system. We're not going to have to break anything into components. Good news. So here we go. Let's deal first with the y direction of the 1 kilogram object. The y direction is, quote unquote, the easier direction because there is no acceleration in the y direction, meaning that the sum of the force components in the y direction will add up to 0. We didn't choose a plus direction based upon acceleration because there is no acceleration, and so for simplicity, or at least to make it feel natural, we're going to choose up as the plus direction for the y coordinate. Meaning that the sum of all forces in the plus direction is simply N1, that's the only up force. In the minus direction is 1g. And as we said before, since there's no acceleration in the y direction, the sum of the forces in that direction is 0. Now, examining that equation, we find that that equation has only one unknown. That one unknown is N1. And so we simply solve it out. N1 is equal to 1 times g, which is 9.8. And the units for any force are newtons, so N1 is 9.8 newtons. First of our 5, and that was easy. It's not going to remain exactly that easy, but nonetheless. Having finished the y direction, the next thing we have to do to complete our analysis of this free body diagram is to analyze the x direction. The x direction, we did make a preference for the positive direction. That will be to the right, meaning that tension 1 is to the right. In the plus direction, the minus direction has 0.2 times N1. We've already solved for N1. It's 9.8. And that is going to be equal to the sum of forces equals m times a. The mass is 1, and the acceleration is a. We don't know the value yet, so we just use a variable. This can be simplified a little bit by multiplying the 0.2 times the 9.8. That's going to give us 1.96. So we'll have tension 1 minus 1.96 is equal to a. Great, except that has two unknowns. We don't know the acceleration yet, we don't know tension 1 yet, and so what I'm doing is I'm going to put a box around it so that I can save it for later, because we're obviously not done with our analysis. What is it that we haven't done? Well, we haven't dealt with the 2 kilogram object, and we haven't dealt with the 5. So let's get to it. Looking back up at the 2 kilogram object, we notice that the 2 kilogram object is going to result in a slightly more complicated free body diagram than the 1 kilogram object. It'll be a little bit more complicated because it's not only in 2 dimensions, but it's also along an incline. As a result, before we wind up writing our equations, we're going to need to take some components. Again, we will begin our free body diagram by drawing a dot. The dot will represent the object itself. There it is. That dot represents the 2 kilogram object, and it's time to name any one force acting on the 2 kilogram object. Well, the first one anyone thinks of is gravity. That's going to be 2g in the downward direction. The next one we think of is the surface force. The surface force is because the object is in contact with the surface, and as always, surface forces have two components. One of them that's for sure is normal to the surface, and that's going to be in this direction. We're going to be calling it N2, so as to not confuse it with N1. And the other one is friction. Looking back for a moment at the problem itself, we see that the 2 kilogram object is going to be sliding up the ramp, driven there by the 5 kilogram hanging object. As a result, since the friction opposes sliding, the friction is going to be down and to the left. So, all surfaces have the same mu k in this problem, so that's going to be an amount 0.2 times N2, whatever N2 turns out to be, in the left direction. Finally, this object is attached to 2 strings, each one of which pulls. String number 1 provides tension 1 pointed down the ramp, and string number 2 provides tension 2 pointed up the ramp. Adding those to our free body diagram, it gets a little bit crowded, but we'll be fine. Tension 1 down and to the left, tension 2 up and to the right. Whew. Let's think about it. Did we include everything? We included gravity. Good. We included the contact force at the surface in 2 components, perpendicular and friction. And we included the fact that 2 strings are tied to this object, so we're all set. Next step in every free body diagram is to align the coordinate system. And again, we use the same principle every time. We always align our coordinate system with the acceleration because that results in the simplest possible equations that can be removed from the free body diagram. Looking once more at the picture, we see that the 5 kilogram object will go down, therefore the 2 kilogram object will go up the ramp on an angle, and therefore we wish to define a coordinate system that is tilted. It is not horizontal and vertical, but rather it is along the ramp and normal to the ramp. And the plus direction will be upward along the ramp because that's what we know is the truth for this object. It's going to slide up along the ramp. All right, we're almost ready to begin extracting our equations from this free body diagram, except there's one complication. Out of the 5 forces that are drawn in this free body diagram, one of them is not aligned nicely with the coordinate system, and that one is the gravity force 2g because it doesn't lie along the coordinates. So before we begin, we're going to need to break the gravity force into 2 components, one of which is along or parallel to the x direction, and the other which is along or parallel to the y direction. So here we go. I'm going to begin along the y direction, and beginning at the top of the vector, I start drawing a component downward until finishing the triangle is done with a component that is parallel to the x direction. So these 2 components, in fact, do lie along the natural coordinate system we've chosen. One of them is along the perpendicular to the ramp, and the other is parallel to the ramp. Now, what we're going to have to do is we're going to have to get an angle inside this triangle in order to figure out what are the values of the components. Neither one of them is as big as 2g. Each one is a fraction of 2g. And you can already see it coming. One of them is going to be multiplied by a sine. The other one's going to be multiplied by a cosine. Cute trick. If you look at the problem as it was given to us, you will find that there is a triangle which has been denoted. This triangle, as all good triangles are, is a right triangle, and it has 30 degrees in one corner and 60 degrees in the other corner. The interesting piece of information that I need to tell you is that every reasonable and meaningful triangle in this problem is going to have 30 degrees, 60 degrees, and 90 degrees. The components we've drawn at this point have an obvious corner that's 90 degrees, because that's where we have the 2 components perpendicular to each other, as good coordinate systems are perpendicular. And what we really need to figure out is whether the 30 degrees is at the top, leaving 60 at the bottom, or the 60 degrees is at the top, leaving 30 at the bottom. Well, Here's the cute trick. The cute trick is, as I noted, every meaningful and reasonable triangle is 30, 60, 90. The 30 degrees that we're given is the angle between the ramp and the horizontal. Clearly, our x-axis in this problem runs along the ramp, but there's not a single line in this diagram that is horizontal. So you know what I'm going to do? I'm just going to put one in. Ta-da! There's a horizontal line. Now that I've done that horizontal line, we see all manner of triangles in this problem, kind of cute. The first one that we know of is that with a 30 degrees over here and a 90 degrees over there, there's 60 at the top. Cool. Oh, here's another triangle. If we were to follow the x-axis and come down to here and then follow the green line that we added, we have 30 here, we have a 90 here, and so we have 60 in that corner. On and on and on. You can use any route through these triangles to figure out where's the 30, where's the 60, where's the 90, and every one of those triangles is a 30, 60, 90. However, the interesting one is the one that includes gravity in its two components. So what I'm going to do is I'm going to note that this angle over here is 30, meaning that that one is 60. Since that one plus this one adds up to a total of 90, what I can say is that the 30-degree angle is indeed located at the top of the triangle, so that 30 degrees is here. That then gives me the ability to very quickly figure out which side is cosine, which side is sine, and I do so by noting here this side is adjacent to the 30-degree angles, therefore this is 2g cos 30. This side is opposite to the 30-degree angle, it's going to be 2g sine 30. And I'm all set. When I go to do my free body diagram analysis and extract the equations, 2g will not appear alone in any of the equations. The normal to the coordinate system, normal to the ramp equation, will have 2g cos, and the one that is along the ramp will have 2g sine 30, meaning I'm ready to go. Now, just for simplicity, I'd like to call these the quote x and the quote y direction. We'll put quote y at the top, and so I'll analyze that first, the quote y direction. Because there's no acceleration perpendicular to the face of the ramp, this will be sum of the forces equals 0, and I have no preference for the plus direction. So I will call it in the quote up direction, meaning that n2 is the positive component. The negative one is this 2g cos of 30. And looking at the free body diagram, that seems to be it. The acceleration in the quote y direction is 0, and so this gives me a complete equation. Looking at that complete equation, there is in fact only one unknown. The only unknown is n2. And so n2 is equal to twice g cosine of 30. And according to my calculations, that gives me 16.97, which I'm going to round off to say that N2 is 17 newtons. Excellent. We have now solved for the second of our two unknowns. We know N1, we know N2. We're not done with this free body diagram, because in order to be done with this free body diagram, we have to do the second coordinate. In this one, we do have a preference for the plus direction to make sure that the variable a in all of our f equals ma equations is actually the same number. We always make sure that it's positive, meaning that to the right or up the ramp is our plus direction. The only force in the plus direction is T2, but there's a whole host of them in the minus direction. There's T1, there's the frictional force, which is going to be 0.2 times the 17 newtons that we got in the previous calculation, And finally, there's going to be 2g sine of 30. Well, sine of 30 is a half, and so twice a half is 1, so that's going to be minus another 9.8 newtons. And the sum of the forces in the x direction is equal to m, which is 2, times a. That equation can be simplified slightly. And I'm going to put a box around that equation because I don't have enough equations to solve the problem out. Looking at the previous equation in a box, we notice that this says T1 and A are two unknowns. Here we now have T1 and A as well as T2, so we've got two equations and three unknowns, meaning that we are clearly not done with solving this problem. So let's head up and see what we haven't done. What we haven't done is the analysis of the last of the three objects, and that's the 5 kilogram object. So, first step in every force problem is free body diagram. This dot will represent the 5 kilogram object. The first force on the 5 kilogram object is 5g downward. The next one is tension 2 upward. The 5 kilogram object is simply hanging in midair, and so because of this, we will not be having a surface force, so there'll be no normal, no friction, and in fact, that's the end of our free body diagram. It's only one dimension, so we will align our coordinate system with that dimension, and we will select plus in the direction of the actual acceleration. Remembering that the 5 kilogram object moves down, we will select plus as our downward direction, and then proceed with writing the one and only one equation that comes from analyzing the y coordinate from the 5 kilogram object. The force in the plus direction is 5g. In the minus direction is tension 2. And as always, sum of the forces is m times a. The mass of this one is 5. That's 5a. And we place a box around it. At this point in the problem, we have now collected three equations, and we have a total of three unknowns. Two tensions, one acceleration, and so those three equations can be solved simultaneously. Let's see if we can collect these equations together and give them a little closer examination. Now that we've collected the three equations together, we can check whether the three equations are consistent with one another. Since we always chose the plus direction to be with the acceleration, we should find that the tensions which always pull are listed twice each. Once in the plus direction and once in the minus direction. Looking at tension 1, in the blue equation it's negative, in the red equation it's plus. And looking at tension 2, in the blue equation it's plus, and in the green equation it's negative. This is a double check that you can do before you proceed with the algebra to decide whether the equations are at least plausible. And they certainly seem to be. They reflect the fact that we were careful with our coordinates. Now, because of this fact that each tension appears once with a plus and once with a minus sign, there's a beautiful piece of algebra that can be used to eliminate the tension from all three equations. We simply add them up, total the left-hand side, total the right-hand side, and the tensions will cancel in the process, leaving us with only the following terms. 5g minus 26.8 minus 1.96 equals 5 plus 2 plus 1 is going to be 8a. The only unknown in this equation is the acceleration, so the acceleration is going to be 5g minus 26.8 minus 1.96 over 8. And I get an acceleration of 2.5 meter per second squared, which is less than g, and so at least that's plausible. There's no way you're going to take a system like that and get an acceleration greater than g. Now that I've got my third answer for the acceleration, what I can do is plug it back into one of my final three equations to solve for tension 1, and then similarly to solve for tension 2. The simpler of the three equations are the red and green ones. The last red equation is the one that I can use to find tension 1. Tension 1, therefore, is equal to A, which is 2.5, plus 1.96, which is 4.49, or we'll call it 4.5 newtons. And selecting the green equation, we can solve for tension 2. Tension 2 will be given by 5g minus 5a. And according to my calculations, I get 36.5 newtons. One nice check for a hanging object is that we know the 5 kilogram object is going to be accelerating downward. Therefore, 5g must exceed tension 2. And according to our equations, 5 times g, which is nearly 50, is certainly bigger than 36.5 newtons, meaning that we have solved for all 5 unknowns, and that's what the problem originally asked for.